Hello everyone. I'll be giving a short talk. I tried to combine most of the elements that were vital for this course, which is hyperbolic geometry, and also the kind of exploration nature. If we go and see how we can progress, what we can come up with, and how we can solve a problem, and also the visual nature. There won't be any big formulas on the board, but there'll be quite a few pictures, and we'll visualize the result. Okay, so unfortunately, no notes. No, but since hyperbolic geometry is part of the course, I think it will be a good addition. So what I want to talk today is the moduli space of either complex structures or curves. Complex curves. It doesn't matter. We can use these interchangeably. So moduli space of either complex structures or curves. Yeah, this is an important object in many areas of mathematical physics. Well, moduli space. What's a moduli space? It's a geometric object that represents all the possible objects of some type. For example, here we'll be talking about all the curves of genus G, and we'll try to represent them and look at all this set as some geometric object. Okay, so we will need a very powerful theorem that I'm not going to prove because of lack of time, and it's not that interesting. So that's basically the only thing you'll have to believe me about. The other stuff will be kind of evident. This is the uniformization theorem. That states that any let me just that any connected and simply connected Riemann surface, so it's a complex manifold of complex dimension 1, can be conformally mapped to one of the three models. The first being CP1, or the Riemann sphere. The second being the complex plane. And the third being the open unit disk. Again, on the complex plane. So it's kind of sphere. This is just the complex plane, and this is just the unit disk with the boundary removed. Okay, so an important theorem that again I will not prove, and will not even comment on the proof. But the idea is the following. So these three options, geometrically, they're very distinct. Look, this is the sphere. This is the basic model of a two-dimensional manifold with positive curvature. A plane is the same but for a zero curvature. And the disk, well, we know how to conformally map a disk to an upper half plane with the real line excluded. And we know that on such a space there is a good metric which is geodesically complete, the hyperbolic metric. So basically, these three options, they correspond to spherical geometry, flat geometry, and or like parabolic and hyperbolic geometry. And this third, it will be the most interesting for us today. Yeah, but to discuss some stuff about this third option, we'll need some intuition from two, which will be easy to get because flat geometry is like very intuitive for us. Okay, so a corollary of this theorem is the following. So here you can see that I'm discussing only simply connected Riemann surfaces. Why on earth would that be interesting? Like the most interesting surfaces are like elliptic curves, which are like tori, right, and other stuff. Why simply connected? Well, because for every non-simply connected, you can just look at its universal covering, and it will be simply connected. So basically, this is what these three options are: models that can cover any Riemann surface, connected Riemann surface. Okay. So how do we get from the covering back to the original Riemann surface? Well, the idea is that any connected, but not simply connected, not necessarily simply connected, Riemann surface has the form one. It's well, just CP1. 2 is C quotiented by a lattice, which is a discrete subgroup of the translation group, and also on two generators. Let me just say here, lambda is just a discrete subgroup of, and I'll say just all automorphisms of C, which are affine linear transformations. Here, I could have written the same thing. CP1 quotiented by some discrete subgroup of automorphisms of C. However, like, oh yeah, and also, sorry, there's another thing. This should be freely acting. So the actions should be free. No fixed points for all the elements except for the identity. And we can see that in the automorphism group of CP1, it's the Mobius group. And as we know, the Mobius transformations of CP1, for each of them, there is a fixed point. Say for translations, the infinity is fixed. For rotations, the zero is fixed. So here there is just no subgroup of the automorphism group that acts freely. Just no options. But here, in automorphisms of C, which are of the form like Z goes to AZ plus B, we can see that, well, if B is not zero, then, yeah, if, for example, if A is equal to 1 and B, yeah, if A is equal to 1 and B is non-zero, then this is indeed a free action. Okay, and the third option, basically the same thing, but here. here we want the disk quotiented by, I'll write gamma, and gamma will be the same thing. It will be a freely acting discrete subgroup of automorphisms of now the disk. So it's the same thing of automorphisms of the disk. By the way, how do automorphisms of the disk look? Well, that's the same as it's isomorphic to the automorphisms of the upper half plane, and we know that this is SL to R. This will be important to us. This is SL to R. Okay, so again, these two important results, we'll keep them in mind. I will not prove them, but let's just keep them. Okay. Now this is just one. There's just one option here, CP1. Here, C over lambda. There are like basically two interesting cases where lambda is a discrete subgroup generated by one translation. So it's just Z going to Z plus something. Let me write it 2 by I and I. And in this case, a map Z goes to e to the Z with this kind of quotient, which guarantees that this map is 1-to-1. This makes this quotient into a Riemann surface that is equivalent to C star. So just the complex plane with the zero removed. Yeah, so that's a very simple Riemann surface. And if lambda is generated by two translations, so a lattice, that's more interesting. That will be a elliptic curve or like a torus topologically. Yeah, and we'll say that for the compact case, this is just a sphere, it has genus 0. This would be, again, a torus of genus 1. And here, here things get kind of interesting because all the other Riemann surfaces, except the sphere and the torus, they all lie in this large class. So here I have G greater than equal to or equal to 2. So this is so this is what we'll discuss today. The idea is the following. So I started with the moduli space of curves. So here we just have basically one curve, CP1. So the moduli space of curves of genus 0 is not that interesting, it's just like a point. The moduli space of elliptic surfaces, so of the form C quotiented by some lattice. That we'll have to discuss a little bit, but basically it is what's important to know about it. It's that it's one-dimensional. There's one complex parameter that completely that determines the curve up to automorphisms. And yeah, so let me kind of write it. So we have genus and we have dimension of moduli space of curves of this genus. So for 0 we have 0, just 1 point. For 1 we have 1, again complex dimension. And for G greater or equal to 2, here, this is actually 3G minus 3. Why am I writing this out? Well, because how do you usually get this number? Like the usual way people arrive here is by looking at some Chern characters and applying the Riemann-Roch-Grothendieck formula to compute some dimension of some tangent space, to or the first dimensions of the first homology of some tangent bundle. But this is kind of complicated. And the idea of today's talk is to get this number in a much simpler way, kind of geometrically, to just see how it appears. Okay, so this is the goal for today. Okay, so first, to get this number, we'll have a bit of a warm-up. We'll get this one by geometric means. Okay, so here's how we'll do it. Here I said that every elliptic curve, every kind of torus, has the form C quotiented by some lattice. Yeah. So let me just draw it. And our lattice is some like this. And clearly we have this kind of structure going on. Okay, so we can look at this part here and say that this is our fundamental domain for our Riemann surface of genus 1, and has the following property. Every point in C can be has a representative inside this parallelogram, right? So here, this is equal to this, and this is equal to this. Yeah. So, and basically, how we're taught to visualize the Riemann surface without any kind of quotienting, we just take this side and glue it to this side, and take this side and glue it to that side. So we get, first we get a kind of a short cylinder, and then we get a torus. I hope that's a familiar picture for everyone. Okay, so here a torus is like a sphere with one handle, and this is exactly what this G equals 1 represents. We have like one handle. All right, but the idea was to kind of get that the space of these tori, different tori, up to orthomorphisms, is one-dimensional. How do we get it? Well, the idea is the following. Like, look, how did we, what kind of, let's look at this fundamental domain, and let's just count the dimension of the space of choices of this fundamental domain on C. I'm not going to fix like any points. I'll take it anywhere. Perhaps it's this one, or perhaps it's like here. This would also be a nice fundamental domain for some torus. Okay, how do we count it? Well, there are 4 points, right? So I can say that there are 4 times 2 real parameters to determine the points. But after that, I know that there is equality of the opposite sides, right? And that's obviously 2 real conditions, just 2 equations on length. So I subtract 2. But then I also have the freedom of automorphisms of my complex plane. because I know that all of these curves, they are distinct up to automorphisms of the appropriate model. So as we already mentioned, the automorphisms of the complex plane are of the form A z plus b, where A and b are complex numbers, and A is non-zero. So basically it's translations, rotations, and homogeneous scaling. Okay, so this allows me to move my fundamental domain around. And using those two complex or four real parameters, I can, what can I do? I can move every fundamental domain such that one of its corners is at 0. Then I can also rotate it so that one of its sides is along the real axis. And then I can also scale it so the length of this side is 1. And that's a way, one of the ways to use up all the parameters of the automorphisms group. Okay, so once, I already mentioned that it's the automorphism group is 4-dimensional in real terms. So I just subtract 4 to get rid of this automorphism freedom. And the result that I get is 8 minus 2 minus 4, it's 2. And 2 real, that's 1 complex dimension. So this is how I get this 1 in a very kind of visual and quick way. All right. So any questions about this part? Here, like the intuition about moving stuff around and adding constraints is needed to proceed.
Yeah, I have a question.
Yeah.
When you consider the torus case, you consider the freely acting actions like translation,
right,
scaling, and no scaling, I think.
Yeah, but here, if we want free action, then basically we want no fixed points, and the only way for there not to be a solution to this equation is for A to be equal to 1.
Yeah.
So this is our action. So out of the 4-dimensional automorphism group, we are left with a 2-dimensional translation subgroup, and our lattice should be a subgroup, a discrete subgroup of that subgroup. Okay?
Okay, but here you use the equivalence of this torus is depending on the whole automorphism of.
Yeah, I used the fact that basically, like even here, every Riemann surface can be mapped to, like, say, C, but C itself has automorphisms. So a coordinate Z and coordinate AZ plus B for non-zero A, there's no tangible difference. So basically, I'm remapping, I'm changing coordinates here, like before quotienting out. And since here I use kind of continuous symmetries, and here it's just a discrete subgroup, which does not affect the dimension of the modular space. It just affects its kind of shape and topology. So that's why this automorphism group acts like here, before quotienting out. That's why I use the entire subgroup, the entire automorphism group.
Okay, so in the G greater than 2 case, you also mentioned SL2R, right? SL2R is the entire automorphism.
Yes, yes, exactly.
Yeah.
This is the entire automorphism group, but as we will see, the free action, like every element of this automorphism group, acts freely. No fixed points.
For example, if we have 4 real numbers A, B, C, D, and if we solve the fixed point, there are 2 cases. One case is there are 2 real fixed points.
No, wait. So, in the case of SL2R, let's just look at the automorphism group of the upper half plane. Just recall how it works. There are 3 transformations. One is scaling, right? Z goes to lambda V, And this obviously has no fixed points, right? Because the real axis is excluded, so 0 is excluded. So for non-unity lambda, this has no fixed points. Then the second transformation is z goes to z plus a, right? This obviously also has no fixed points. And the third transformation, yeah, well, it's a bit, well, let's just look at, right, the third transformation is a composition of a inversion, shift, and again, inversion. Okay, yeah, I think we can see that there are no fixed points for inversion plus shift plus inversion. Here's how we do it. So let's take some point. Then after inversion, it will be somewhere here. And you take some shift. And this shift will oh yeah, it will just so the first inversion keeps it on this ray. Then a shift changes the ray for any point in on the upper half plane, except for the real points, right? So now I'm on a different ray, and the inversion now moves it to like this point. So basically, this third type of transformation changes the ray. That's why it's acting freely. Do you see it now? So once again, this is kind of first here, then here, then here. And since the intermediate action, the shift, changes the ray,
it also might not change the ray, right?
Accidentally. In what scenario?
Like this shift vector is parallel to
this, because here the shifts, here A is real. The shifts are always horizontal. That's why the only ray that is parallel to the shift is the one that coincides with the real axis, but it's excluded. We don't have such ones. Does this answer your question? So basically, this third type of transformation, it's a sort of a rotation around 0, but a kind of that shifts the radiuses, the radii around. But the rotation part guarantees the freedom of action. So, returning, so basically we've covered the genus 1 case. Now let's go to the higher genus case. First, the first thing that I would like to kind of generalize is, or modify, not generalize, modify, is the construction of the compact Riemann surface from some fundamental domain through gluing. So in the genus equal 1 case, this was just some parallelogram on a plane. Now, in the higher genus case, the plane should be replaced by either the disk in the Poincare disk model or by the upper half plane. I'll draw the upper half plane because it kind of gives a little bit more space on the board. It's less restricting. So basically we have the upper half plane, and here we need to quotient by some discrete subgroup to acquire some compact surface. So let's not think in terms of these discrete subgroups of SL2R, which are called Fuchsian groups and which are kind of hard to visualize. We'll return to those when they're needed. But let's think in terms of gluing. So here's how we got like a sphere with one handle. How would one get a sphere with two handles through gluing? Well, I think here's how one can visualize it or kind of arrive at it. So here, first I'll notice that this gluing was not just this side to this side, but also with this orientation of this sort. Right? And now I'll kind of open up this parallelogram, like cut it along one edge, along one vertex, and I'll draw it like this. So basically, here's something, then here's my parallelogram, which I kind of cut. Okay? So what happens when I try to glue it? Well, you will see that basically what we get is yeah, so this is my new figure. After I glue it once and twice, what I'll get is this sort of figure. Do you see it? Well, basically I kind of opened up a small hole in my previous torus. All right, but so this is one handle. So from this point, I think it's kind of almost obvious how to get like two handles. Well, let's just make this part, which I did not specify, into another copy of the same parallelogram with its own gluing rules. So basically, now I'll open it up a little bit, and this will be the original four sides, which were glued once again. In this fashion. And the second part will be which are glued in the same kind of fashion. So I'll just copy these blue marks here, but in red. Like this, and like this, and like this. Okay? Now, a simple kind of if you just picture how it's glued, you'll see that this is precisely a thing with two handles. Let me, I guess, help it a little bit. After I glue these two pairs, I'll be left with this sort of thing. So after I glue these, I get here just a one copy, and here again just one copy. And here, since all of this circle should be glued to this guy, we can see that these points, actually, these 2 points, should also be glued together. Yeah, sorry about that. Now we'll have a better picture. So these two points need to be glued together, and we'll have this kind of picture. And we need to glue this guy with this guy guy with data. And we can see that when we do it in this fashion, this is precisely what we get, a sphere with two handles. Sorry about the confusion. Now it's correct. All right? Fine. So the result of all of this, let me erase this uniformization theorem, because we've basically used everything from it that we need. Yeah, so hopefully I've convinced you that gluing a 8-gon now produces a Riemann surface of genus 2. Now it's easy to generalize to arbitrary genus G and realize that what we actually need as a fundamental domain is a 4G gon. So let me So I want kind of 8 points. And I want them to be connected by geodesics. And geodesics are also circles that have that are like arcs that are perpendicular to the sides. So basically, I have kind of like this. This. Okay. Yeah. Now when I glue, and once again I glue it in this fashion. Let me. I'll write it as following. So say I start here. This will be the side which I'll call A1. This is the side B1. Then, since this is glued opposite to this one, I'll call this side, because it's basically the same side, I'll call it A1 inverse. And because this side is basically this side but inversed, I'll call it B1 inverse. And then this pattern continues. So I'll say that I'll have A1, B1, A1 inverse, B1 inverse, then A2, B2, and so forth, until I have AN, BN, oh sorry, not N, G. G inverse, B, G inverse. Yeah. So this is the sequence of my sides. All right. We're almost done because now we already have a way to calculate like the first part of this dimension formula. Here's how. How many ways are there to place, how many coordinates do we need to place 4G points on some two-dimensional thing? Obviously 4G times 2, so it's, once again, so 4G times 2, that's 8G. Now, in the case of in the G equals 1 case, if we wanted to glue those sides, they had to be equal length. Here, it's the same thing. Yeah, since we want to glue those sides, they have to be equal length. So A1 and A1 inverse are obviously the same length, and so forth. They're not, so, they're just the same length, and that's why we have as many relations, real constraints, as we have pairs of sides. But since we have 4G sides, that means we have 2G pairs of sides, so we need to subtract 2G. And here we notice that this is already 6G or 3G in complex terms. Nice, so we already got this 3G. The last part is this minus 3, and it's complex minus 3, so it's real minus 6. So how do we get it? Well, 1 minus 3 is easy to get. It's the same minus 3 as this one minus 4. So we basically use all of our automorphism group to fix something. For example, we can fix the position of one of the, say, from this initial point. That will use up 2 parameters. And then we can also fix the direction of the first side. We don't have 4 parameters, so we can't fix the length of the first side, but we can at least fix the direction. So we can use the automorphism group to acquire this minus 3. This, I'll write that this is from automorphisms of the disks. Okay, another condition. And here how it appears. Well, here let's look back at the torus case. Once we glued this parallelogram like sidewise, let's look. So let me just draw these red and blue sides on the resulting figure. So I claim that there is only that these 4 points become 1, and this red side is, for instance, this cycle of the torus, and the blue side is this cycle of the torus. Okay, I guess that's pretty believable. So basically the moral is that all of these angles all add up here to form 2 pi. Well, otherwise there would be a convex singularity here. That's definitely not something we want in a smooth manifold. Here, we want the same thing. We want all of these angles to add up to 2 pi. So that would kind of prompt you to just subtract 1, because the angle, just the sum of angles, is just 1 constraint. But here we need to be a bit more careful. So I've written out these sides in this way because I want to look more precisely at the process of gluing. What is gluing? Basically, gluing is saying that there is some automorphism which brings this side to this side. In the case of g equals 1, this was just a shift by this blue vector. That would bring this red side to this red side. And this, for the case of the blue side, it was the shift by red vector. Now if we take some point on this parallelogram, say this 0 point, and then we try like taking it around our parallelogram, like by applying first the first gluing transformation, then the second, then the inverse of the first, then the inverse of the second. So I'll write it as A, B, A inverse, B inverse. We will obviously get identity, because this is just a commutator in an abelian subgroup, because translations are just abelian. So there is definitely like no result of this kind of transformation. However, in the SL2R group is non-abelian. And the subgroups, the discrete subgroups we're interested in, are also non-abelian. That means taking some point, say this initial point, along different transformations, along these transformations inside SL2R is a non-trivial operation. It is not necessarily identity. So if I denote, by some abuse of notation, denote these transformations by the same letters as the sides, I'll write this thing as the composition of multiplicative commutators of all of these transformations. And I'll think of this action as taking our point along all of these sides, or equivalently, like along cycle, and another cycle, and back again, and back again. And this is an element in SL2R. Well, strictly speaking, it's an element of this subgroup gamma. But additionally, it's also an element in SL2R. And I want this element to be identity. That contains basically like two constraints. One is that it is an identity in terms of rotation. So that would precisely mean that the angles here sum up to 2 pi. It's the same thing, requiring that angles sum to 2 pi, or that this product of commutators does not have a rotation part in it. So if we start here by some basis, after we take it around, we return to the same basis. It's the same rotation. And also, there is a condition, since it's an element of SL2R, which is 3-dimensional. The other 2 dimensions, they correspond just to the position. And they say, basically, that our initial point is the same point that we return to. So, even though in terms of sides it may be kind of obvious, but these are not sides. These are some transformations in SL2R which correspond to sides. So we shouldn't think of them as kind of always leading to exactly the initial point. Yeah, so basically this is a condition inside SL2R, and since SL2R is 3-dimensional, 3 real dimensional, that means this condition is equivalent to 3 constraints. Basically, you could think that in this case, our constraint was that after applying this commutator of transformations, we not only arrived at the same point, but also had no rotation and no scaling. But again, it is kind of not very clear here because the group is commutative, so it kind of not an interesting condition. But here, this condition is interesting, and it is exactly 3-dimensional, so this is 3 constraints. And that's why we subtract another 3 here, and finally arrive at the 6g minus 6, or 3g minus 3 in complex terms. And that is the dimension of moduli space of curves of genus higher than or equal to 2. And sorry if I took longer than expected, but that's what I wanted to tell you today. Questions, by the way, about this second part?
It's very interesting, very intuitive. What I learned is to the twist coordinate, you give a very different proof.
You mean
the 6g minus 6?
Yeah.
G minus 3, yeah.
Yes.
What I learned is that on a surface, you can decompose surface into pans like you drew, and then you have twist along the gluing. You also have the length of the gluing curve. Those are roughly also 6G minus 6 parameters.
So you mean kind of twists along these?
Yeah, take two pans, right? Like the length of the pans curve, and also when you glue them, how much you twist. Those are the parameters of the modular space, of the technical space. But you give a very different proof.
Yeah, I guess this twist corresponds to kind of the angle between these vectors. So
yeah, you're right. Yes. Yeah.
Yeah, because we can always choose this kind of fundamental domain, right?
Yeah.
But there would be a non-trivial gluing here.
Yes.
On these sides, there will not be a kind of just translations. Yeah.
And if we do twist, like what you say, if you do twist, then the vertical guy like shears.
Something like that.
Like you said. Very cool.
Okay.
Where did you learn this?
So basically, I saw some short note in some Telegram channel about this.
Telegram.
Yeah, about so this 4G gluing. I've seen it in some literature before.
Okay.
And then I saw that by considering these 4G guns on a hyperbolic plane, half plane, we can kind of force these angles to sum to 2 pi, which is impossible for a 4G gun on a plane.
Yeah.
If you try to glue it on a plane, you will always end up with a conic singularity, which is also kind of easy to track, but it's definitely not a smooth manifold. So if you want to get a smooth manifold, you need to do it on a hyperbolic half plane or a disk. And since I kind of had a good grasp of how to go from parallelograms to this one, just from the study of elliptic curves. That means there should be an analogous way going from this 4G glance to this 3G minus 3, and basically I just needed to fill in some details with the help of some literature.
Okay.